Okay, so part of triangle and proofs, we're looking at positioning a figure in the coordinate plane. So it asks to position a square with a side length of 6 units in the coordinate plane. So what we actually need to do is, so I'm going to draw my, so ideally we're going to look at just quadrant 1, and we're going to choose points that are positive because they're easier to work with. So if I was to draw something with 6 units, this is my point here, and I can say this is 0, 0. So I'm going to count up 1, 2, 3, 4, 5, 6. So this is at 6. So this coordinate is going to be 0, 6. And my square is going to be 6 units across, and it's going to be by 6 units. So this makes it easier. Now I know this coordinate here must be at 6, 0. And this point here, this is going to be at 6, 6. So by placing this right against the axes on the coordinate plane, it will make it easier. So we have to make sure we put to the corners so we can use the 0. Okay, so this time position a right triangle with leg lengths of 2 and 4 units in the coordinate plane. So I'm going to look at using quadrant 1 where it's positive. So this is at 0, and 1, 2, 3, 4, and across 1, 2, and we'll say 3, 4 there. So what I can do is draw my triangle against the vertex. So it's easier for me to use for the coordinate. So this is going to be at 0, 0. So this point here is at 2, 0. And this point here is at 0, 4. Okay, so write the coordinate proof using coordinate geometry. And we're given a rectangle ABCD with coordinates at A is 0, 0, B is 4, 0, C is 4, 10, and D is 0, 10. And prove the diagonals bisect each other. So we need to, if we had to draw this, so this would be on our coordinate plane. And we have, so this is at 0, 0. So this is point A. B is at 1, 2, 3, 4, 0. So this is B. C is at 4, 10. So that's 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's actually by here. So we'll just move this. And this is coming down here. So our points, we have C is at 410, so this is 410. And this is point D, which is at 0, 10. So we need to prove, let's just redo that, that's at 0, 10. And we need to prove that the diagonals bisect each other. So this means that these diagonals, they bisect. So this is what we're going to do. So we're going to use what's called the midpoint formula. So we can actually prove that this line here and this line here, they actually meet at the midpoint here. So use the midpoint formula. So we need to, so the midpoint, we're going to look at AC. So we're looking for this point here, AC. So we need to add the coordinates. So we're going to add the x coordinates. So that's 0 plus 4. Let's change my pen. It's in a pen. So 0 plus 4. And we need to divide by 2. And then the y coordinates, we're going to do 0 plus 10 and divide by 2. So this is going to be 4 divided by 2. So this is going to be 2, and 10 divided by 2 is 5. So my midpoint of the line AC is at 2, 5. So now I need to do the same for my other line, BD. So BD, our points are 4 plus 0, and we're dividing by 2. And the y is 0 plus 10 divided by 2. So we have 4 divided by 2 is 2, and 10 divided by 2 is 5. So we can see that they both have the same coordinates. So we can therefore say that the line AC is congruent with BD. And so by the midpoint, and they both have the same midpoint of 2, 5, the diagonals bisect. Okay, so we're given a rectangle, PQRS, and we need to prove that the diagonals are congruent. So let's label our coordinates. So S is at 0, 0, and R, this is at 1, 2, 3, 4, 5, 6, 7, 8. So this is at 8, 0, which means Q is going to be at 8, 4, and P, this is going to be at 0, 4. So we need to prove that the diagonals are congruent. So we're looking to prove that the distance from these diagonals are actually the same. So those diagonals, we want to prove that they're actually congruent. So we need to prove that SQ is congruent to, so this is what we're doing, proving that SQ is congruent to PR. So to do this, we need to use the distance formula. So we need to use the distance formula, which is the difference in the x coordinates plus the difference in the y coordinates. So if we write down what values we have, so we're right over here. So S, the point S is at 0, 0, and Q is at 8, 4. So this is x1 and x2, y1 and y2. And we're going to substitute them into our formula. So x2 is 8, and x1 is 0, and that's squared. y2 is 4, and y1 is 0, and that's squared. So the distance, 8 squared is 64, and 4 squared is 16. So the distance is going to be root 80. So we'll just leave it at that for the minute. Now we need to look at the line. So we have P and R. So P and R. And the points, P is at 0, 4. And R is at 8, 0. So this is x1, x2, y1 and y2. And we're going to use the distance formula again. So this time we're going to do it for, and this is for line PR. So the distance, so x2, so that's 8 minus, and x1 is 0 squared. And y is 0, y1 is 4, and that is squared. So 8 minus 0 squared is 64, and minus 4 squared is 16. So we have the distance of root 80. So because the distance between both lines are the same, that means we can prove that, so we can say S, so we've written SQ. So SQ, we said is, this was SQ here. So SQ is congruent to PR because we have the distance of root 80 is equal to the, or congruent to root 80. So we've proved that they are congruent. So the diagonals are congruent.